Hello everyone, it's July 28th. Alright, let's take a look. Anything of concern? Alright, let's go right into it. Beautiful array. This seems to be something I might have done before. So for some fixed n, an array num is beautiful if it is a permutation of the integers, such that for every I smaller than j, there's no k with k's in between, such that nums k times 2 equals nums I plus nums j. Given n, return any beautiful array. Hold on. For any two positions, there's no position in between with this, such that nums k, so in between, twice of that equals to this plus this. Okay, so which means for every ij, so let's say ij is here, there's no k in between, that 2 of this equals to this plus this. Given n, return any beautiful array. Okay, so let's see. 4, n equals 4, so we have 1, 2, 3, 4, any permutation of 1, 2, 3, 4. So we want is for any given pair, right? So we have 4 positions for any given pair, and apparently I and I plus 1, that's not a pair because there's no k in between. So what we're going to do is I and I, like 0 and 0, 1, 0 and 2, 0 and 3, right, 1 and 3. Yeah. So for any such pair, we need to guarantee that the sum of the two values will not be equal to k, double the k. Sum of two values will not be equal to k double, right? So the k can only be in the middle, right? That's the k value. K value is in the middle because the k cannot be on the outside, which means if we double every value, so 1, 2, 3, 4, we double everything, it's 2, 4, 6, and 8, right? Which means we need to find two values, right? Two values such that the sum of the remaining will not be equal to this. So we're trying to see if we can identify the first and the last. Yeah, that doesn't feel right to me though. So the sum of these values. Hold on. Double, right? Double means it's an even value. So maybe the easier way to think is if we can make everything to be odd. Well, that's not possible. We cannot make everything odd. But okay, even plus even is even, right? And odd plus odd is also even. So it has to be even plus odd. But that's not possible. We have to have even plus even. Hold on. So all size. There are different strategies that we can do. Like we can say the front and end we put into an even number, right? And an odd number at the front and end. Once we do that, it's guaranteed that everything in between is good, right? So once we do that, for every even number, so from 1 to n, we can count how many even number there are and how many odd number there are, right? So given 5, we have, given 4, we have 2 evens and 2 odd, right? So we have, so if we do even odd, then that's not going to work. On 4 positions, right? And then if we have 1 even and odd, right? If we go, this is odd and this is even, like we satisfy the first one, even odd and even odd, that's good. Second one, even odd, that's fine. Well, this one is fine, so we can just do even, odd, odd, like 2, 4, 1, 3. That one will work because everything is going to be even and odd, so that one is fine. So what if we have a lot? I mean, even and odd, front and back. Let's say we have 6 values, right? And because this one will have to handle this, 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 and this. Now we have 3 odd values. Let's just say we do half even and half odd. Half even and half odd, we eliminate a lot of issues. Like at least half of the situations. Because for each value, if you think about it, we say any pairs, right? Any pairs. So for any pair, front, right? So for the value in the front, we have n minus 2, right? We have n minus 2 different things we need to worry about. And among these, if we do all even and all odd, then at least half of this we don't have to worry about. The only thing we need to worry about is the front half, right? The front half, and we have even plus even, and there's also the even in the middle. So when that happens, if we can guarantee, right? If we can guarantee, so basically we're saying we transfer this problem, right, into a subproblem that saying given an array of values, and all of them are all evens, or all of them are all odds, what is the likelihood? What is the strategy to create a beautiful array? Now, if we are all even values, right, then we want to make sure that twice of the ones in the middle does not equal to the sum on both sides. Well, since they're all even, we can divide them by 2 and then become even and odd again. Does that work? Hold on. So 6 will be 2, 4, and 6, right? Well, 2, 4, and 6, if we do 2, 4, and 6, that is going to be not, because 2 plus 6 equals 8, and 2 times 4 is equal, so we need to do like 4, 2, 6, something like that, right? 4, 2, 6. So if we rearrange it, 2, 4, 6 is 1, 2, 3, right? And for 1, 2, 3, we want all odd and all even. So it'll be 2, 1, 3, right? And in this case, 2 is by itself, 1, 3 is 2, so we're actually good. Because given 3 values, that's the only arrangement, right? Now for odd, no, not for odd, for odd values, so we have what? 1, 3, 5, right? When 1, 3, 5, so we go through the same process. All odd values. Now odd values we can plus 1, then it become even values, right? It actually is the same arrangement as previous. It's the same arrangement. right? So the previous we rearrange, it's going to be 2, 1, 3. We say we'll put all the even on one side, all the odd on the other side, and that come out as 4, 2, 6, right? So the remaining should be 4, 2, 6 as well, but they have to be odd. So we minus 1. That's going to be 3, 1, 5, and this one shall work, right? Yeah, because anything once you touch the odd, then it's always right. It is just within themselves. Let's try 5. 5 is an odd value, so again, 2, 3, 4, 5. Now when it's odd, we have one more odd than even. So we have 2, 4 on one side, 1, 3, 5 on the other side. So when that happens, we split into 2. Then 2, 4 we don't have to worry about anymore because they're only 2, so we don't worry. So 1, 3, 5, we do the same trick, right? 1, 3, 5. So what we're saying is we're gonna find. Let's put odd on one side and even on the other side. And then when even is only 2, we don't worry about it. And then when odd is this, then we rearrange. We plus 1 and divide by 2, which this one give us would be 2, 6 plus 1, so 2, 4, 6 divided by 2 will be 1, 2, 3, right? So 1 becomes 1, 2, 3. We rearrange again 1, 3 on one side, 2 on the other side, and then that is good because that's 2 and a 1, so that's good. So now we going back, we have but what if I have more on the other side? Let me think. Maybe we can just leave 5 as is in the middle. No, we cannot. We cannot leave 5 as is, but in the middle. Are you saying we have to do the same on the other side? Let's say we have a longer one, and we have to handle on both sides. And my idea is if we handled on one side, right? If we handled on one side, then the other side shall be able to handle as well. Interesting. Let me think. The other side. So on this side we handled. It's going to be 1, 3, 2, which translate into when it's going to be times 2 minus 1, right? Times 2 minus 1 will be 1, 5, 3. So on this side, 1, 5, 3. So on the other side, it should be 1, 3, 2 as well. So we multiply by 2, it's going to be 2. 1 plus 1 is going to be 2, 4, and no, it's be times 2, times 2, times 2, times 2. So it's 2, 6, and 4, right? 2, 6, and 4. But we don't have 6, so we just remove that value. Yeah, I'm not sure. I mean, let me think. It might be slightly different. The way we rearrange it. I mean, if it's the same number, then it's the same arrangement. But if it's not, then on the other side, it will be a little bit less, right? A bit less. It will be 1 less value. Let's do a longer. Let's do a 7, right? 7. So again, 1, 3, 5, 7 on one side, and 2, 4, 6 on the other side. So 1, 3, 5, 7. We need to rearrange this, so this one becomes plus 1, plus 1 divided by 2, so it'll be 1, 2, 3, 4, right, on this side. On the other side, we divide by 2, it's going to be 1, 2, 3, right? So we're going to rearrange 1, 2, 3, 4. That's going to be rearranged to 1, 3, and 2, 4, right? And 1, 3, 2, 4, we're good. On the right side, we need to rearrange to be 1, 3, and 2. Oh, this means 1, 3, and 2 even goes first. So we just remove the last. Yeah, we remove the last. Like 1, 3, 2, 4, and that's on the left side, we repopulate back. It's going to be times 2 minus 1, 1, 5, 3, 7, right? And then we remove 7, remove the last value, and then going to the right side, it's going to be 2, 6, and 4. In this case, we have 1, 2, 3, so it'll be 1, 3, and 2, right? And we remove it, that's going to be 2, 6. That's not right. We don't have a 6. Huh. Ah, it's because 3 is the largest. Hold on. I feel like I'm almost there, but still there's something not right. Yeah, because I want to save, but maybe it's fine. Maybe we don't save. We just, I mean, the easiest way we just we just do it on both sides. Like if it's even, then we can copy it. That's fine. If it's not even on both sides have different numbers, so we just do on the other side. But I just want to see if it's possible to make it easier. Right? 1, 2, 3, 4, 1, 2, 3. Let's try. Not going to move 1, 2, 3, 4, 5, and then 1, 2, 3, 4. Right? In this case, we have 1, 3, 5, and 2, 4. Right? And this one will be 1, 3, and 2, 4. Yep. The value we need to move is different. So we need to remove the 5 position. But the 5 position. So we say we gonna remove whatever the 5 position is. We're gonna remove it. We identify which one is missing on the right side, and we remove that value. Will that work? I mean, whatever it is on the left side, we rearrange. We identify. Like if it's 1, 2, 3, 4, and 1, 2, 3, we identify 4 is the odd one, right? And we arrange on the left side whatever we rearrange, and that's the largest one, so we can always remove it. So this situation is fine, we're good. Now the situation that's a bit tricky is a 1, 2, 3, 4, 5 on one side, and a 1, 2, 3, 4 on the other side. When that happens, so when we rearrange, I mean, that's gonna be 1, 3, 5 on the left and 2, 4 on the right, right? So they're gonna go through a lot of changes. Would it matter if we remove 5? Which means what we'll be looking at is a series of values, right? And the difference is in 1, 3, 5, the other is 1, 3. So this one's going to rearrange however it is. We're going to rearrange. And after we rearrange, after we rearrange, the 5 will go to somewhere else. Right? The 5 will go to somewhere else. Basically, we're saying rearrange 1, 3, 5 or rearrange 1, 3. So we're going to reconstitute this into 1, 3, 5 reconstituted, we're going to become 1, 2, 3, right? Now 1 is 1, 2, 3. Oh, this might be a recursion. This might be a, yeah, 1, 3, 5 will be reconstituted to 1, 2, 3 because we can just do 5 divided by 2 plus 1, right? And 1, 2, 3, we know the result of 1, 2, 3. The result of 1, 2, 3 is going to be 1, 3, 2, right? The result of 1, 2, 3 is 1, 3, 2. Oh, I think, hold on, we can build it up. We can build it up. So n equals 1. If it's 1, then it's just, if 1 and 2, we just return. So n equals 1, which is return 1. 2, which is return 1, 2. 3, right? We can return, we can do the rearrange 3, right? 3 is actually the base case. It's going to be 1, 3, 2. That's the base case, 1, 3, 2. Okay. Now 4. 4 is 1, 2, 3, 4, right? And then we say, okay, we rearrange it to become 4 is going to be 1, 3 on one side, 2, 4 on the other side. Now 1, 3 is 2. So this one will go out 1, 2, and 2, 4 will go out as 1, 2 as well. And once we get out, we can reconstitute them. So how do we reconstitute them? Now reconstitute them by times, on the left side and be times 2 minus 1, right? So 4 going to give us 1, 3, 2, 4, right? 1, 3, 2, 4 is on that. Now 5 we're going to go, it's 3 plus 2, right? So we got 1, 3, 2. On the right side is 1, 2. So 1, 3, 2 will reconstruct times 2 minus 1 times 2 minus 1. 1, 5, 3 times 2 minus 1 times 2, 2, 4. I think this works. All right, let's give it a shot. Let me do 28. All right. I mean, this won't be hard to test case because there are a lot of values, and I am only finding basically the easiest way to do this. So I'm not going to test on our own. We're just going to do it. So this is going to be a DP table, right? DP table is going to be, oh, how is a DP table going to be? It's going to be this. Going to start, 0 is this, right? 1, 2, and 3. 1, 2, 1, 3, 2, right? And then we say for I in range 1, 2, 3, 4 all the way to n. We're going to do divided by 2, right? I'm going to say left and right equals to I divided by 2 and I minus I divided by 2. If I add 2 is 2, it's 3, so I want to go right is here and left is here. right? So we have left and right, and then the left is going to be reconstituted. So the left, left list is going to be dp left. Actually, we can directly do this. It's going to be dp left, right? dp left is the left part, and the left part is going to be times 2 minus 1, right? So I'm going to say j in this, j times 2 minus 1, that's that, plus on the right side is going to be j times 2, let's say, yeah, j times 2 for j in dp right. Actually it's fine. I just want to say right and left. Just spell out right, left. RT and nah. I like RI and LE, left and right. So this is going to be dp dot append, right? And append this. So once we're done, we return dp n. All right. Not sure. We can actually check. We can check, but it will be different. The check will be different. Yeah, let's check. So the tests is going to be list range from 1 to doesn't matter, whatever I say 1 to 10, right? And then we say for, so redo this, for I, n, right? In test, enumerate test. So actually in enumerate test, res equals beautiful array n, right? Once we get, we need to check. So we need to write another function for def check answer. So check answer, we're going to get a result, which is a list of integers. We need to return a Boolean value, right? So how do we check? We just do exactly that, right? It's going to take a long time to do, but it's fine. So for I in range, len res, actually going to minus 2. For j in range, I plus 1, I plus 2, for len res, right? And for k in range, my god, I plus 1 to k, to j, right? So in this, we're going to say if res I plus res j is equal to res k times 2, will return false. Otherwise, return true. Right? So we get the result, and we say if check answer res, let's say it's pass, otherwise fail, then we need to, we don't have answer, we have result, and the test is going to be n. Okay, so run it. Oh, whatever that is was wrong. Right, we all pass. Let's try a 100. Took a long time, but we pass. 1000 is going to take a long time to check, but I think we're good. All right, submit. Pending, judging, accepted. Yep, so that is the solution. So there are two levels of thinking, right? So there are two hoops to jump. Right? first we need to figure out a simple way, right? A simple mechanism to achieve a beautiful array, right? A beautiful array. Now my method is to aggregate, to group all even or odd numbers on the left side and all even numbers on the right side. This way, any interaction between the two sides are guaranteed to satisfy the requirement, because even plus odd equals odd, which does not equal to 2 times some value. Next, we need to figure out how to organize the odd part and even part of the array. Since all odd numbers are on the left side can be transformed into an array. We can let's do this. Suppose the odd part has largest value O. I don't like O. Largest value M. Then we can perform value plus 1 divided by 2, right? On all the odd numbers, and on odd numbers, this will turn the odd part into an array starting from 1 to m plus 1 divided by 2. Now this is a repeated problem. We have solved this problem already. We have solved this problem already. I've solved this problem. Turn the odd part into an array starting from 1 to this. To find a beautiful array from 1 to m plus 1 divided by 2, we actually have solved this problem already. Similarly, on the evens part, right? On the even part, we can perform value divided by 2 to convert into an array starting from 1 to n divided by 2, where n is the largest even number. And this problem has been solved as well. Thus, we can use bottom-up DP solution to acquire one beautiful array for any given n. So the runtime is going to be O n, and within this we have to do this, and that's O n squared. That's O n squared. Maybe it's possible to do it. No, because we're storing this, so I mean, we can reduce the space complexity, right? Because we only need divided by 2 and divided by 2. Huh. That's actually no. So we don't know when we're going to use it. I mean, we can say that if it's yeah, we can reduce a little bit, but it'll be hard pressed to say we can reduce it. So O(n) squared. That's O(n) squared. Let's see. Oh yeah. Terrible runtime. Oh my god. There's an easy way, much easier way. Alright, O(n) squared run at 305 milliseconds. I do not even see. It's too far. It's too far. Alright, it's too far. Very, very bad runtime. Okay, so that's not the way to go. Interesting. Which means the correct answer is O(n). Can we make this one faster? I think the idea is legit. It's just, we create an array, and we create it. Every time we have to create 2 arrays, and I have to merge them together. That is taking a long time. Hold on, let me think. So given any value, we split into 2. Well, that's fine. And for each one, we can split into 2. Right, this we split into 2. Everything we split into 2, so that's going to go O log n. And the merging cost, that should be O(n) log n, right? But why is this one so slow? Interesting. I was expecting it to be O(n) log n. But a bottom up is not O(n), and this is not log n. All right, let's try O(n) log n. So we given a value, we split into 2, right? Left part and right part, and then we do left part and right part. What we're saying is that we don't process the left part or right part. Like, how do we not process it? Which is fine because we know the n value, right? We know the n value. That's good enough. Right, that's good enough. Then we call this again. This one will give us, so we split into 2, this one split into 2, and it will end with 0, 1, 1, 2, or 3, and we give a value, and we merge. Well, maybe we can do it O(n) log n. Let's try. Why is the bottom up? That's probably the wrong way to do bottom up. So this one, we try O(n), right? So we give an n and we need to know what is the transformation. Right? We need to know the transformation. So the transformation is, what is the transformation? Hold on. So this level, we go down, right? We get it, and then we transform. It's gonna be. Yeah, I was trying to avoid the transform issue earlier. So, right, if we have this, we know this is gonna be 9 plus 1 divided by 2. It's gonna be 5, right? So we were looking at 1, 2, 3, 4, 5, and then that's the level we're looking at, and then 1, 2, 3, 4, 5, we're gonna transform, right? We cut into 2, and it's a, I don't know, man. Yeah, we divide into 2, and we can use memorization to handle it. So divide into 2, that's going to be 1, 3, 5, and 2, 4. Right, so this one going to be 1, 2, 3. This one going to be 1, 2. So boom, done. This one I'm done. Right, this one I'm done. So when I'm done, I go back. What I return is a 1, 3, 2. So this one I get 1, 3, 2. And I know because I am odd, so I need to turn back into 1, 3, 1, 5, 3. And this one can turn into 2, 4. Right? And then from this, going back, how do I convert this to this? It's all going to be odd value. So we merge them together, right? 5, 3, 2, 4, we merge them together, and we do a transformation for all of them. So 1, 9, 1, 9, 5, right, 3, and 7. Then we transform up. Okay. I still don't understand why this one will be faster. Or maybe it's not. So the initial, right? Initial. What is the transformation initially? Well, we can say the initial transformation is nothing. Because it has to be either even or odd, right? So we put them together, and then we're going to transform back. We just don't transform initially. Now when you set up, hold on. Yeah, I think we do have to set another function, def dp, right? Def dp gonna be num, so we don't, and is gonna be whether it's even or odd, right? That's the from even, right? It's gonna be a boolean value, and this one gonna return a list of integers, and we're gonna cache this. So from func tools, import ARU cache. So cache this at ARU cache match size equals none, right? So with this, now I can try. We give a number, right? And from even, so we given a number. So we say if num is let's say equal to, if num is equal to 1, right? Turn this. Oh, that's not. It depends, right? Yeah, it's. Oh, what do we do? We cannot just return because we want to rearrange them. Because we give, so eventually we'll go down to 102, then I get the result, and the one I return, like if it's from even, then I shall return 2, right? Hold on. Yeah, so it's 1, 2, 3. So that's a 3. We should return 1, 2, 3, right? We shall return 1, 2, 3. And if we return 1, 2, 3, and then they handle, so that's going to be, because we push in is 5, so we return is this. Yeah, I think this is true. So if it's 1, return 1, right? If num is equal to 2, then return 1, 2. If num is equal to 3, then return 1, 3, 2, right? That's that. And then we're gonna do left equals dp. So given a number, right? Left is gonna be dp dp num minus num divided by 2. Right, that's gonna be left. And left is gonna be false. And right is gonna be dp num divided by 2. That's gonna be true from even, right? So left and right are lists. Now we're just gonna merge the list. Right? How do we merge? Well, because the left is, so left and right will become the right thing. Now we merge them together and then use from even or from odd. That doesn't feel right. If we press 1 and it says from even. Like if I pass 3, num is 3, right? And it's from even. That's not 1, 3, 2. That's gonna be something else. Right? And then what if we pass in 3? Yeah, what if we pass 3? From even, from odd, or alright, so I think this one, yeah, we have to consider from even. If it's from even, it's true. Like if from even, then the one return shall be 2. Right? Else shall return 1 from odd. Right? If it's from an odd. And it's going to be 2, 4 if from even, else it's going to be 1, 2, right? So it's going to be 1, 3 if it's from odd. And this one, if from even, else it's going to be, no, even is going to be 2, 6, 4, or 1, 5, 3 from odd, right? So I do left and right. After left and right, which are giving me the right one, and I just put them together, right? So when I return, v times 2 if from even, else v times 2 minus 1 for v in left plus right. So I'm not sure, man. This feels so weird. So the return value is going to be dp n minus n divided by 2, that's going to be false, plus dp n divided by 2, that's going to be true. I'm not sure. Solution 2, let's go range 10. Max recursion. Oof. Why would I have max recursion? If num equals a num not equal to 1? Huh? I don't understand. Let's say like if it's 3. Oh, dp 1. 1 is having trouble. How? How is 1 having trouble? 1 minus 0, so dp 1, false. And dp 1. Oh, that's a 0. Ah, so we have to have a 0 case. Num equal to 0, that's going to return no matter what. Oh, it passed. Okay. That seems to be faster. This is 538. 550. Let's try this. It is correct. All right, try it again. Let's just see. 1,000. How fast can you run 1,000? 45 milliseconds. How about this one? $152. Wow. So this is the solution. Bottom up is not working. Well, I shouldn't say it's not working. I think I did it wrong. Yep, that's the right way to do it. There we go, 41 milliseconds. So this is O n log n, divide and conquer with memoization from LRU cache. So So same idea as solution 1, but much faster. Clocking at 41 milliseconds and 27% ranking. All right, this is something I like to see. Now we can go for the solution. Medium question, no, I've not done this before. 932. So 932. High acceptance. Divide and conquer. Yeah, this is supposed to be divide and conquer. Medium question. A lot of people don't like it. Why? Divide and conquer. Memorization. Let's go here. Memo, def fn, if not, odds equals this, even equals this, return memo. This answer is quite unintuitive. Wait, hold on. I don't even have to do divide by 2, and then I just reconstitute it, and then return this. Then we call fn directly, so we don't have to even say from even or from odd. Hold on. I don't have to say from even or from odd, which means if the left comes in, right, a DP number, right? DP number, and as I'm going through, I will go the odds, I'll go the even, right? Even, odd. So get even and odd. And when I return, I turn it back. But in here, I offload it to something else. I say the ones you give me shall be already transformed. I don't have to because I just do this part, I do this part, whatever value you give back to me, and I will turn it into, yeah, I don't understand why I do it this way. It doesn't really matter, right? If it keeps going down, it doesn't matter because I always do the n, right? I always do the n. It's only one something, every time. Yeah, because every time it's one. It's like, yep, every time it's one something, and then can convert back. And if I'm looking at when, all I want is fn, right? I get fn, and I retrieve whatever it is on this side. Because I do not care intermediate. The intermediate value, I got the intermediate value correct, but I don't really care about the intermediate value. All I care about is I will divide the array into two parts, right? And the left part will give me some return value. The right part gives me some return value, and I convert it back, put it together, and then we're good. And on the left part, right, it doesn't really matter. It doesn't really matter. Yep, I like this. All right, so I call this better implementation, right? It's a better implementation. So solution 3, I think we can ARIO cache directly here. Yeah, I think we can catch it here. So we say better implementation of divide and conquer. So yeah, n, we say if n is equal to 1, and return 1, else we can say beautiful array, we say left equals beautiful array, self, right, self dot beautiful array, n minus n divided by 2, right, and it's just n plus 1 divided by, just n plus 1. Yeah, n plus 1. N plus 1 divided by 2. That's the right way to do it. Right is self dot beautiful array, n divided by 2. Right. And then return this plus this v times 2 minus 1 for v in left plus v times 2 for v in right. And I think that shall do it. Yep. Bad implementation. We can directly area cache on this. All right, try this one. Yeah, 32 milliseconds, even faster. 32 milliseconds, 92%. Yeah, I was thinking too complicated. I said, you don't need intermediate value. Why do you worry about intermediate value? It's just straightforward. You have an array, we cut it in half, right? And the left half we're going to pass an n, the right half will pass an n. I don't care. Just like whatever that's given back to me, that just in order. And I just need to reconstitute it, and then we're done. All right. Let's see what people's complaint is about. Too hard. That's all right. 2020 is last year. Probably during a competition. February, August, April, July. Now I don't know. Yeah, it's just regular divide and conquer. I mean, I didn't thought about it. I start with a bottom up, which is easy to write, but this is O(n) squared, so it's very slow. We can divide and conquer, but this is just too ugly divide and conquer. This is a beautiful divide and conquer. O(n). Wait, the divide and conquer is O(n)? It is O(n). Oh, it is O(n). Imagine case 105. We have 52, 53, right? And this. No need to solve a problem. For 13, we can do it only once. And most 2 values. At each level, we have 2 values. At each level, like O(n) log n depends on we have to do every single level. But if we memorize, then at each level, we do 2, and eventually we will hit. There's some branch we don't go, so each basically we're saying each n is computed once. Yeah, each n is computed once. Each is computed once. But what about this? Every single one has to go through this. That's the part I don't understand. I think that you're saying it's O(n) squared, which is not. Apparently it's not. I'm getting confused. Right, the merging cost. This is the merging cost, is O(n), right? And we go log n time. The level is log n time. But it is true that some of the branch we don't have to deal with. Yeah, each level is O(n) if we want to merge it, and we have log n levels. That's how I visualize it, right? Have log n levels, like in this, right? So this one, that's one level. We can keep going down, right? Keep going down, and each level is O(n). This is O(n), but we don't have log n levels, so O(n) log n. But what he's saying is, after we reach a certain level, right? Like we computed this, we don't compute this, which means in this level, right, the merging cost is just this and this, right? Because this we need to compute and merge. This one no merging, this one no merging as well, no merging. So we directly come back, and so we just merge it once here, and then we come in here, we have to merge this one, we merge this one, and these are all, remind you, these are all different values, right? So we merge this, merge, and then merge. So this merging is O(n). This actually already merges not O(n). It's just half, right? It's half. And this is even less. So each level, so what we're talking about is n plus n over 2, the merging cost. You done it? Well, it scared me a little bit, but awesome. And n divided by 4 and plus n divided by whatever, and then we have log n of this. Oh, I can see this is O(n). Yeah, because this is basically just 1 plus 1 over 2 plus 1 over 4 plus 1 over 2 to whatever power. And if we extend it to infinity, this thing, I think it's approaching, it's basically just 1 over 2 plus 1 over 4, like all of that. That is not going to be, so basically it's 1 minus 1 over 2 to the power of n divided by 1 minus 1 over 2. Yeah, so that's going to be 2 if we go. Actually, I'm not sure. So it's this one plus 2. I don't remember. Yeah, that is going to be 1. So yeah, that's O(n). Yep. Ah, Lord, this is good. This is good. So this is not O(n) log n. Update. update with memorization, the runtime is ON. See explanation below. In solution 3. Alright, so about the runtime. Without memo, each the merging cost of each level is ON. Right, but with memo, only the top level has ON cost. The subsequent levels has ON divided by 2, ON divided by 4. Right, cost, because we do not have to compute for each node. Right, we don't have to compute for each node. This means the total complexity is ON plus ON divided by 2 plus ON divided by 4 plus plus ON divided by 2 to the log. Just to 1, right? To 1, which this will not exceed O2n. Hence, the runtime is the time complexity, not runtime. The time complexity is ON. Yeah, and a volt. At most 2 values in the recursion tree. Yeah. Yeah. Analysis on time complexity. Wow, this is like the 3rd day in a row we got a time complexity one. I mean, this one is ON squared. Yeah, because merging cost for this, each one is, I mean, it's like it's 4, 3, all the way to n. And then we have to add them together as ON squared. Right, divide and conquer. I thought divide and conquer is the same and almost equivalent to bottom up, but no, divide and conquer can be faster. You know what? I want to try one more thing. Just kind of proof. If we don't memorize, right? Don't memorize. Let's see what's going to happen. That does sound like ON log n, right? That's sound like there's ON, that's ON log n. All right, that's it. That's it for today. I'll see you guys tomorrow.